Welcome, I'm KR, and we will be exploring a new series of videos that will be a very light crash course to quantum computing. This series of videos is meant for my friends in my university to help them understand a surface level overview of quantum computing. But I think it will be nice to also release this on YouTube. In the next series of videos, we will be exploring topics that can help you understand what quantum computing is. For you to understand this course, I'm going to assume a lot of things about you because it does take a lot of concepts and blends them together into one course. Where you're going to be required to know a bit of algorithm design, linear algebra, complex numbers, probability, computer architecture, and that's about it. So, yes. All right. For this first video, we'll be trying to see what does computing mean and a brief history of how classical computers lead to quantum computers. Now, what exactly is computing? Computing, essentially, is the manipulation of information through a computer. And in terms of classical computing, it means to compute through machines that use classical binary digits or bits. Now, what are binary digits? They can represent any sort of information that can either be yes or no, on or off, and it is or is not. We can operate on these bits using some logical operations like and or not, and represent them through circuits, such as these circuits right over here. By combining circuits together, we can create all sorts of computational devices that can help process some mathematical operations that such as this full adder right here. So we can do addition, multiplication, division, exponentiation on a classical computer. Now, these circuits are really very small. Now, let's take a quick history on the development of these circuits. So we have a sort of timeline right here that showcases the development of these circuits. Starting in 1971, we have the Intel 404. It was the size of a human cell, approximately 10 micrometers, or about 10,000 nanometers. And it was one of the most very, let's say, revolutionary chips out there because it was the first 4-bit CPU. Now, let's go to the next generation. In 1984, this was the advent of the Intel 3086, and it was the size of a small bacterium like E. coli, around that range. It has a feature size or technology node of 1 micrometer or 1000 nanometers. This was the first x86 computers, which is around 32 bits. The next generation would be around in 2003. It will be the Intel Pentium 4. It was roughly the size of a one of the largest viruses out there. It has a size of 0.1 micrometer, which is around 100 nanometers. And it's a very popularly used microchip for very low end computers right now. But for actual modern computers, like in 2005 right now, whatever chip that is being produced by Intel, Apple, and other sorts of microchip manufacturers, their technology node here is around less than 10 nanometers, which is insane. For each generation of microchip, we essentially uh, do a 10 times reduction of their technology node size, their transistor size, in order to achieve better computational power. We can see it right here, like this graph pointing downward. And based on this pattern, we can see a, let's say, a dead end on the wall. Because at some point, you're gonna have to reach the size of atoms and electrons. And what governs those worlds? That is quantum effects. The problem with quantum effects is that the nature of quantum matter is very fickle. An example would be electrons doing quantum tunneling across barriers that were set up by us humans. Quantum tunneling can lead to uncertain results because it can basically um, lead to unordering uh, ways of quantum tunneling can lead to uncertain results. And because of that, quantum effects do not mesh well with classical computing. So what do we do with these quantum effects? What do we do as a society? Well, instead of eradicating these quantum effects, let's why not embrace them? Why not harness them to our advantage? This is the offer that quantum computing offers. It offers that if we can use quantum effects to our advantage, it can lead to monumental speed up to our computation. It uses quantum bits to process information, and it embraces the three main properties of them, which is superposition, entanglement, and decoherence, to calculate new algorithms, or rather construct them. Since it is based on quantum physics or quantum mechanics, one odd attribute to quantum computing is that operations are unitary. When you do one action, you can always reverse them when the same one is applied, making computation to be reversible, very unique to quantum computing. Quantum computers promise to solve certain problems faster, such as factoring, unstructured search, and simulation of quantum systems far faster than any classical algorithms that we know. While a lot of algorithms were able to leverage more on three quantum phenomena, the real power comes from the fact that quantum algorithms use linear algebra and complex vector spaces in order to search for new, novel ways to approach solutions. This new mathematical framework of using transformations and interference that are available and quite widely seen in quantum mechanics allows novel solutions to exist that are not possible in binary logic. That is itself based on, for example, and or not. It mimics the power of parallelism using the power of Pythagorean's theorem. While in classical computing, you're limited to a certain range of solutions because on the fact that quantum computing is basing itself on linear algebra and complex vector spaces, you're able to promote the probabilities of getting the right answer and find new, let's say, spaces to explore uh, solutions that are not possible in classical but are very possible in quantum computing. To put it in an analogy, coming up in this series, we're gonna explore some key topics that can help you understand at least a surface level detail of quantum computing. These are going to be quantum states and qubits, the nature of quantum gates and reversibility, and the nature of quantum computation. That's for our big picture. Next, we'll see why reversibility matters and how it helps us prepare for quantum logic.